Welcome to the Early Career Researchers webinar series presented by the Informs Junior Faculty Interest Group. The series seeks to increase the visibility of research conducted by junior faculty and senior PhD students within the field of OR and MS. So please follow our Twitter and LinkedIn accounts for subsequent webinars, and please let us know if you're interested to present. Today, we're very happy to present two talks given by Dr. Sara Shashaani from the North Carolina State University and Dr. Ann Hesson from the Georgia Institute of Technology, respectively. First, Dr. Shashaani will present her talk entitled Monte Carlo-based machine learning. Dr. Shashaani is an assistant professor in Edward P. Fitts Department of Industrial and Systems Engineering at NC State. Her research interests lie in the intersection of stochastic simulation and data science. She's also a co-creator of an open source library called SimOpt. Dr. Shashaani, we are honored to have you present in this webinar. The floor is now yours.
Thank you so much, Rui. It's very nice to be here, everyone. Thank you for your interest in my research. I'm going to give a quick disclaimer. So because I know the audience is going to be coming from very different research backgrounds, I have kept the talk at a high level so that it can really be intuitive and informative for many of us. But I do have a link here if you wanted to read a little of the details and the technical things that I haven't included in this talk. Rui, will you remind me of the time? Okay, thank you. All right, so I'm sure even though we are coming from very different research backgrounds, perhaps we all are pretty much aware of machine learning, right? Over the past 50 years, there has been a lot of amazing developments in the field of machine learning, and it has specifically been in the past decades, maybe with progress with these deep learning neural nets and so on. We have seen that it can be capable of doing really, really great things. But there are some issues always with machine learning. There is always, you can always question lack of rigor there, flexibility, and in particular, when you have higher dimensional data or a system that has more non-stationary characteristic, as well as some, as I've mentioned here, discrepancies at the data that can actually disrupt the learning. So here's, in my view, kind of a short map of what's really going on. So when we are collecting the data, at the point of time, we're going to be using the empirical distribution of that data to inform the data-driven model, and then use that as well to assess how well that model is doing. And we know that the data can be changing, right? So for instance, if we had data collected that was going to show us what's the frequency of the rain, as we know with climate change, that frequency is going to change, so that the empirical distributions that we were going to be using initially for data may not really apply for the frequency of the rain in the following years. But that's not the only issue. So that's the issue that I'm calling input uncertainty, and I'm going to dig a little bit deeper into that when we go to the future slides. But I also argue that it's not just the frequency of the rain that's changing. As a result of that, the logic in the system, the patterns that machine learning is trying to identify can also be changing, right? However, the sort of the assumption, the underlying assumption for many of these frameworks in the machine learning world is that the pattern is going to stay steady. But because of those uncertainties, there's actually biases and variances that can be imposed into the model, and if we ignore them, we can be misled hugely. So here's one synthetic example of machine learning for a very simple problem. So here, since I've mentioned rain, let's say this was a question of choosing between two different lands or sites where a farmer wanted to build a certain structure, right? Like a storage or like a waste storage, let's say. And so since this is synthetic, we sort of know what the true distribution of both of these lands are. And I'm showing them to you with this shaded gray distribution on the right. And if we do have these true distributions, then we would go with, okay, so they're doing very similarly on average, but we can see that land 2 has a higher variance. And so perhaps land 1 is better because it has less risk. We can be more certain about, what should the outcome be from the once we choose land 1, right? And now, since we don't know these two, we're going to go to the distribution of the predictions, right? So we build this machine learning models. And there's a lot of work also that has been done within machine learning about capturing the variability. So that's why I'm showing the variance of this predicted distribution to be very closely following the variance of the true distributions. But if I was going to look at these distributions, so as you see on the x-axis, the probability of waste overflow as a result of choosing land 2 would be predicted to be much lower. And even with that correct estimate of the variance, I would still be choosing land 2 that I know is not the correct answer. But if I can correctly identify the bias that is also, coming from those sources of uncertainty that I mentioned earlier, I will be able to see that, in fact, land 1 is a better choice, and it has much less risk if I incorporate both of these two things, the variance and the bias, right? So this is to illustrate what happens in machine learning, what can be missed. And now my argument for this talk is that we have a much better chance of identifying these bias and variance quantities if we use, if we wear the glasses of Monte Carlo, right? So just to sort of bring us all on the same page, here's what I see Monte Carlo simulation worldview as. Many of you might be familiar with this. So suppose this part that I've put in a box is that simulation, the Monte Carlo simulation, which consists of a generator, random numbers, input random variables that are going to be produced using an input model I'm calling F, and then output random variables that are going to be following this logic model I'm calling H here. So we're going to need these notations as we go along. So that's why I'm pausing on some of these. But now this system is going to have to be evaluated under certain decisions, right, or controls. I'm calling these Z. So you're choosing that Z, you're going to run this model several times, or black box several times, to get several outputs, copies of your Y. And from there, you estimate what your objective function should be at that choice of a control, right? And this is, within Monte Carlo methodology, we have a lot of confidence in this approach because we can use law of large numbers, central limit theorem, to have confidence intervals that we can be very confident about, right? So they are going to be covering that true value with a high probability as we should expect, okay? So now I'm going to walk us through the same worldview in an example so that we kind of get more used to it before I switch to the machine learning case. So let us look at a simulation, a simple simulation problem, an inventory problem. And I am showing this big data set on the left, but really with a simulation, we have some physical knowledge about what this inventory system, how it operates. So we can build the simulation logic that I'm showing with little h again. But something that might be unknown is the distribution of demand. So just also to review what this inventory problem is, you're going to have demands, and your choice is what should be the level of inventory before you order. You put the next order to have enough inventory, and what should be the maximum level that you order. So these are like the SS strategies, right? If you aren't familiar with them. So I'm calling these Z, or my control. And the input model in this case is going to be the demand. That's the random part. So once again, I have my random number generator generating these U's, or random numbers. I run them through my simulation logic to get my output Y of Z and F, which, by the way, you are seeing that I'm adding F here. I'll talk about that in a moment. And then I do the estimation as we should for a black box, right? So from these Y's, I can, of course, look at the confidence interval as I talked about earlier, but I can also look at things like prediction intervals by looking at, different quantiles of these generated Y's. So because I'm using this F here, and I always use this input model, if I am 100% sure that that's how the demand is going to be, then, I would say, yes, this prediction interval is going to very likely cover with 95% what should actually be happening in terms of the total cost under that choice of Z, right? But if I'm uncertain about this F, then there is an effect that F is going to have on this prediction interval and the quality of my output from this simulation. And that's what's called the input uncertainty in simulation. So now back to that worldview, I have added this F at the output, and you can see that it's a condition that I put when I am doing my estimation of the objective. So this is not the objective I'm looking for, right? The objective that I'm interested in is theta of Z. So as a result of running this model, I'm going to get theta of Z given F, or my input model, plus noise. So I'm using epsilon of U to show the stochastic uncertainty, because that's where it all starts from here when I generate these random numbers. But this theta of Z given F is actually random, because if this F is unknown, right? What you can think about this as, having an in expectation really being theta of Z. So I can actually decompose this as theta of Z plus another noise that I'm calling input uncertainty, right? So the epsilon of F. Okay, so now let's just see what I'm talking about. So the actual system, the actual inventory system, is going to have outputs that are this capital Y of Z. In reality, that system is random. So the output of that system is going to be random. And let's suppose that it's following this yellow distribution, right? The outputs from my simulation is going to have a distribution like the green one. It depends on that input model F. And if I repeat this for many different Fs, I can see whether or not the average of those means is going to be aligned where the true average is. And it may not, in fact, always happen, right? So I have written again how I decompose the output of my simulation. The first thing we see is that the variance under acknowledging input uncertainty is definitely not going to be the true variance of the system. So it's going to be larger because we are now having more randomness, more uncertainty in our assessment, in our modeling. But the other thing is you can also have bias if the expectation of specifically this guy, the epsilon of F, is not 0, right? You can see that would cause bias. Right, that's what I just said. Okay, so input uncertainty is a field very well known, and Enhe here and a lot of other colleagues we have in the Simulation Society have spent years on seeing how we can actually evaluate input uncertainty. Bootstrapping is one technique that is used for evaluating input uncertainty, in fact, quantifying the variance and bias due to input uncertainty, and you can You can see with bootstrapping, what we do is if we have a data set that I'm calling D, I can take bootstraps of it and then fit an input model to each of those bootstraps called F with a little star of J, and then get outputs from that input model. And following along with the literature, I can compute the variance of that epsilon of F, and I can sort of do some similar computations to get a measure, or at least have a sense of whether or not there's going to be bias due to the input model. And this, the simplest thing that can be done with the bootstrap is just to compare the average of those bootstrapped distributions compared to the average of the total data used at once. Okay, so several papers here. Some of them are giving a very good review of the whole literature behind input uncertainty in simulation. Okay, now I'm going to move to Monte Carlo, but for machine learning. So think about this problem, and let's assume that we don't really have the physical knowledge. So we don't have that little H I was showing you, and we want to build it from the data that we've collected. So the data is going to consist of, as you see, the cost associated to strategies with given demands. And so I have this input model of all of these three variables. The input model is going to be helping us build the data-driven logic and also evaluating the response, or the Y of Z. So here I am now adding this capital H. So I've switched to capital H because H is itself random in this case, unlike the first case where we knew what the logic is. Okay. Now, one other thing is my random inputs are going to be sort of, as you know, in machine learning, you have something that trains your model, a set that trains your model, and a set that validates it, right? And you want certain properties between these two sets, like they want to be non-overlapping and so on and so forth. So that's how I'm showing this U1 and U2, a set of U2, and U2 is helping me build my model, while U1 is just giving me that output. And here I'm making things a little simple by not going through what happens in validation and so on, because I think it's enough to give the intuition of what the point is. Okay, so back to the same worldview. In this case, like I said, we switched to a capital H. And here I have a typo first. So this has to be Y of Z and H. I'm missing H here. I have it in the next slide, but here I noticed too late that I am having a typo. Okay, but now when I decompose this, I see that, well, this is in fact going to be a theta of Z given the model and given the input distribution. So I have two conditions, right? Two inner conditions. But then, I just follow the same steps as I described before to see that I have these different sources of uncertainty that are associated with the input model, the logic, and the stochasticity. So I'm calling epsilon of H the logic uncertainty here, knowing that it's going to be affected by, part of the data, or the U2 that's being sampled from my input model. And once again, looking at what happens in the output side of things. So now I have input and logic uncertainty. And if I wanted to decompose this output, I see that there are several other epsilon terms here, as we saw in the previous slide. And the difficulty here will be that there is a lot of dependence between some of these noises, right? So for instance, as I said, you want to have a certain relationship between the data that's being used to evaluate the model as opposed to the data that's used to build it, to avoid, as I said, overlaps, or to make it more generalizable as it is known in machine learning. But secondly, we know that very directly the model that is being used, that's being built, is quite dependent on the data that builds it. And then on top of everything, all of this depends on what input model I used at the beginning to do all of these inner steps. right? So just another disclaimer here. When I say logic uncertainty in this talk, I don't mean, you know, if your true logic was nonlinear and you were using a linear logic, like I'm not calling that logic uncertainty. That's typically, in my understanding, what's known as model discrepancy. And I have a very good reference to suggest to you to look at, because that basically says if you are using a different function, like functional, to model your system. So if it was, say, I don't know, logarithmic and you were using linear, how would that affect your outputs, right? So that's a different thing. And we're going to here just assume that the learning algorithm we're using for H is going to be a linear regression, just a simple thing. All right. So the way we tackle this, first of all, it seems to be more complicated than just the typical simulation problem. But if we see the worldview, everything follows as, you know, what we would expect in a typical Monte Carlo simulation. So here, because of this additional conditioning that we see due to the logic, we can actually tackle this by doing the same bootstrapping idea that I was showing you, but maybe going a few layers deeper by doing those conditionings. So earlier I was showing you conditioning on the input model. So it was kind of just at this level where I would for input uncertainty, change my input model, so F stars, and then from them I would get these U's for statistical variance. I'm just denoting them here a bit differently because from them I'm going to further do more bootstraps, but that's going to help me with the logic uncertainty. Okay, I don't know, I see you on, Jenna, you have a question for me, or should I keep going? So you're saying, can you give some examples of logic model H and what types of data you would collect to estimate it? Yeah, so in the, I mean, this is just a pure machine learning problem, right? So if you, in that farm problem, say you have all of this data on the two lands, I don't know, like the quality of the soil, the structure of, you know, the neighboring areas, the rain, the other variables in the climate, and you want to have a logic that's like a linear regression of these variables that's going to predict to you what's going to be the probability of overflow in these, in land 1 versus land 2. Make sense? Yeah, thank you for the question. So, okay, so as I said, I don't have a lot of time. I'm probably running out of time already. So the structure I showed you can be used. There are several techniques that need to be used. For instance, if I go deeper in the layers, that will allow me to have higher order accuracy estimation of the error, right? It can give me better information about the total bias. And I can use things like functional Taylor expansion on the input data in the input model and influence functions to compute these biases. So I'm going to refer you to the paper that I have referenced at the first slide. But some of the other things we do, because this structure looked a bit scary, right? So you're like, I just want one output. Why should I do so many you know, nested samples? The good news is that we can find optimal budget allocations for these layers so that in fact the total number of bootstraps you're using is not going to be scary and, you know, hindering the practicality of it. The other thing we use is something like controlled variant for variance reduction to be able to actually make this more efficient. So I'm just pointing them out because I don't have time to go deeper into that. But now let me actually give you some proof of why this is working, just numerically, right? So this is an example of, you know, I was choosing that in that same synthetic problem I showed you. So I had land 1 and land 2, and I knew already which land was the better one. And if I do the comparison in the general machine learning, so my results are going to be biased while I have taken care of the variance, right? I've made sure that the variance is being quantified and all that. And this confidence interval is showing the difference between the two lands. So what I am hoping to see is that since land 1 is better than land 2, that this difference confidence interval falls entirely above 0, right? If it does, that means I have been able to choose the correct land. And as you see, when I'm not incorporating this bias estimation, I will be ending up with the wrong choice. If I correct for the input bias only, I am going to be, inconclusive, but I won't be able to find the correct choice. So it's helping, but not sufficiently. If I do the input and logic bias correction both, in the case where I have a small data set, it's also inconclusive. So it's still not giving me the correct selection. But if I do that optimal budget, because there's high variance, and I'll talk about this just a little bit more. But if I do the optimal budget allocation, I, in fact, am able to find the correct selection, even with a small data set, right? When my data set is a little bit larger, I see that without the budget, optimal budget allocation, I can still find the correct land. But, it might make sense to be able to take advantage of this optimal budget allocation strategies. Here's one more example. This is a machine learning problem where we have the true value, the true expected value that I'm showing with this yellow line. And these are the prediction intervals. If I was to evaluate, so this is just kind of estimation, right? This is, I'm estimating whether or not, I'm estimating the output, and I want to know if in my prediction interval, the true value lies. So you can see, and I'm changing the noise level, just the stochastic noise level, to see if that will be going to matter. And on the y-axis, the first two choices are the ones that are using the Monte Carlo based machine learning. So you have the biases that I was talking about incorporated. You can see confidence prediction interval is wider, but you can also see that because of this correct quantification of bias, I am indeed able to cover the true value in my prediction interval, right? What's interesting is, so just to kind of see how robust this is, I changed the true logic from linear to polynomial to a more complex to see, because as I said, I'm not really using the model discrepancy here. So I'm just using linear regression, regardless of what the true pattern, the true logic that I don't know was. And, as one would expect, if you have so in the polynomial case and the low noise, all of these techniques are failing to cover the true value. But also surprisingly, even though I'm using linear regression, it still can cover the true value for a lot of these other cases. Even though the pattern is not linear, my linear model can do it, within these prediction intervals. So this was, I repeated this problem many times just to see what would be the correct coverage of these. So how many times would these prediction intervals actually contain the true value? And you can see the probabilities, right? So the proposed technique and the proposed star is the one with the budget allocation, right? Up to the budget optimal one. And so you can see very significantly, including this bias corrected prediction intervals is going to improve the coverage probability. This was with 100 replications. Okay, and so what I talked about was for machine learning, but some of the things, especially about the logic uncertainty, may very well also apply to simulation, right? Because in a simulation also, we have a model that, okay, we can be certain about it, but it's more likely than not is going to be not exactly modeling the true logic of the system. So if we follow the same rules, the same structure of these nested layered bootstraps and quantifying the bias due to logic and input, in fact, here's an example showing you, this is only the averages. So I'm not showing you the confidence intervals on this plot, but this is back to that inventory problem. And I am using the simulation. I'm not using the machine learning, right? And the black line is the true objective, the true expected value, the true expected cost. So the pink one and the brown line are showing me how I would estimate these different scenarios. So sorry, what is the x-axis is those excuse me, the Z, like the control, right? So the strategy of ordering a new inventory when your inventory is 20 up to 40 and blah, blah, right? So the strategy 1, strategy 2, strategy 3, or control 1, control 2, control 3. And I know the optimal one is the middle one from this true expected. And in this case, you can see that when I use so opera is the name I use for our method. I didn't use it consistently throughout the talk, so I apologize. But this is the one that uses input and logic bias correction. And you can see that it finds the correct optimal strategy among these 3, but it also finds the correct ranking of the 3 strategies, right? So if I wanted to know the middle one is the best, but what is the next best? This is also able to find that for me. So it seems to be, with this, even though machine learning was inspiring me to go deeper into like the logic uncertainty, I think it's something that can benefit the simulation itself when we are doing, for instance, calibrations of the model and so on. And to conclude, if we can, look at machine learning from the lens of Monte Carlo, there are several benefits to that, right? We can compute the bias and variance more reliably and have more reliable prediction intervals. We can actually build better models, build better machine learning models. That doesn't mean they have to be more complex, right? Like deep learning. They don't have to be super complex that is hard to understand what's really the major factor or so on. It can be a linear regression, but it is going to be a better model because it's going to generate more robust predictions. And you can leverage other things in Monte Carlo, like variance reduction. We did a little bit of that here. There's more that can be done. We can leverage sensitivity analysis to lower the dimension of the uncertainty space. We can also, one thing that I didn't mention here, you might have come to this question before that, okay, what is the ground rule for how much data do I need for training versus validation? There really isn't any ground rules, right? So we just say divide the data into 20%, 70%, whatever. But this can in fact help us finding those rules for what would be the best way to use the data to have the most robust predictions. And some of the things that we haven't done yet is there's a lot of correlation going on. And there is some parts of those, correlation between those epsilon values that I was showing. Some of them are work in progress. The other thing is, oh, sorry, this line is repetitive. So, but I should say, we can, when we are thinking about building better models, sometimes it's about making the logic more complex, as I mentioned, but sometimes it's about like feature selection, right? So if I have a linear regression and I want to know what features should I keep to build this linear regression and what should I dispose, that can also be, this methodology can be advantageous to doing that more effectively. And finally, the one thing that is like really the big hole here is the model discrepancy part. Although I think even without that, we are seeing some promising things. I do think incorporating that is going to be, you know, yet another helpful component to this kind of new worldview of machine learning. I'm going to stop here. Thank you.